Before the world could understand the language of the stars, it struggled with the language of falling apples. Gravity, so familiar, so ordinary, was paradoxically mysterious. From the earliest thinkers to the great mind of Newton, we accepted that objects fall because they are drawn by an invisible hand, a force acting across space at a distance. One could observe it in the apple that fell from the tree or in the moon that danced around the earth. Yet its underlying nature remained shrouded in abstraction. We knew it worked, but we did not know why. Imagine for a moment the human curiosity at its most intimate and restless. Why does a feather descend more slowly than a stone? Why, when we drop objects of the same size but different weight, do they fall identically when air is removed? These are simple questions, yet they hint at something profoundly fundamental, a hidden symmetry in the fabric of reality, whispering that our understanding of mass, motion, and space itself was incomplete. This itch in the mind of a physicist is not a trivial discomfort. It is the quiet voice that demands, look closer, think differently, trust your intuition, even when it defies the textbooks. Before Einstein, gravity was a familiar companion, yet its explanation relied on forces that acted mysteriously at a distance. Newton had provided us with the majestic law of universal gravitation. Two masses attract each other with a force proportional to their product and inversely proportional to the square of their separation. It was precise, predictive, and elegant. And yet, for all its triumphs, it left a whispering question unanswered. Why should masses attract across empty space? How does the invisible hand reach across the void, instantaneously affecting a distant moon or planet? This was not a mere technicality. It was a philosophical problem that gnawed at the mind of anyone who dared to imagine the universe not as a static stage, but as a dynamic, responsive tapestry. In this intellectual landscape, the spark that would ignite the equivalence principle arose from observation, reflection, and a stubborn insistence on simplicity. Einstein was captivated by the curious universality of free fall. Drop a hammer and a feather in a vacuum chamber, and they land together. Throw a bowling ball and a tennis ball off a cliff, and they accelerate identically toward the ground. It seemed trivial, almost mundane, but therein lay a subtle whisper of the profound. Perhaps the mass that resists acceleration, inertia, and the mass that responds to gravity are not merely proportional, they are identical. Perhaps the forces we attribute to gravity are, in some sense, indistinguishable from acceleration itself. One can almost imagine Einstein walking through the streets of Bern, watching people lift and carry objects, feeling the weight of each step, and musing on how the sensation of weight is indistinguishable from the force experienced in a rapidly accelerating frame. This is where philosophy and physics intertwine. The question is no longer simply, what causes the apple to fall, but rather, could gravity itself be a manifestation of geometry, of how space-time bends and curves in response to the presence of mass? Here, the spark is not only intellectual, it is poetic. The universe is offering a riddle, and the mind of the physicist must listen. The beauty of this spark lies in its simplicity. It does not require a lab full of intricate instruments or a fleet of satellites orbiting distant planets. It begins with thought, with imagination, with the willingness to suspend the ordinary and consider the extraordinary. Einstein's genius was not merely in mathematics, but in his intuition, in recognizing that the ordinary experience of falling, of weight, of motion, holds the clues to the deepest structure of reality. In the apple's fall, in the effortless glide of a stone in vacuum, in the sensation of being pressed against the floor when an elevator accelerates, there is a subtle harmony, a hint that gravity and acceleration might be reflections of the same cosmic truth. This is the spark that ignites the story of the equivalence principle. The realization that our everyday experience, so banal and familiar, is in fact a window into the profound. It is the curiosity that dares to ask, what if all forces of gravity are simply manifestations of how space and time bend beneath our feet? It is the itch in the mind that cannot be ignored, the quiet insistence that reality is more elegant than we have dared to imagine. And it is from this spark, this quiet philosophical unrest, that the journey toward understanding begins, a journey that will take us from the ordinary fall of an apple to the extraordinary curvature of the cosmos itself. If the spark of curiosity is the ember, the thought experiment is the flame that illuminates hidden truths. It is here, in the quiet theater of the mind, that physics transcends instruments and laboratories and becomes a profoundly human act of imagination. To understand the equivalence principle, one must first abandon the assumption that gravity and acceleration are distinct entities. One must step inside a sealed chamber and ask, could the universe play a trick on me, making two fundamentally different experiences feel identical? Consider, if you will, an elevator, a simple box, enclosed and isolated, suspended somewhere above the earth. You cannot see the world outside. There are no windows, no hints from the cosmos. Inside this chamber, you feel the familiar pull of weight, pressing your feet firmly against the floor. Objects you hold in your hands behave as expected. They fall toward the floor when released. You would instinctively say, this is gravity. The earth pulls us downward. But now, imagine a twist. The elevator is far from any planet, floating in the emptiness of space, and it accelerates upward at exactly 9.8 meters per second squared, the very acceleration that mimics Earth's gravity. Remarkably, everything inside behaves exactly the same. Your pen drops, your book falls. They hit the floor as if Earth itself were beneath you. Pause here and reflect on the profundity of this thought. Locally, within the confines of the elevator, there is no experiment you could perform that would reveal whether you are in a gravitational field or merely accelerating through empty space. The sensations, the motions, the very rules that govern your experience are identical. This is the heart of the equivalence principle. Locally, the effects of gravity and acceleration are indistinguishable. What seems like two entirely different phenomena, being pulled downward by a planet or being pushed upward by acceleration, are, in the language of physics, mirrors of one another. The power of a Gedanken experiment lies in its simplicity and universality. You do not need to measure forces with complex instruments or observe distant stars. You do not need satellites or particle accelerators. Your imagination, guided by careful reasoning, is sufficient. In this thought experiment, Einstein demonstrated that gravity could no longer be treated as a mere force acting at a distance. Instead, it must be understood in terms of the geometry of spacetime itself. If acceleration produces effects identical to gravity, then perhaps gravity is nothing more or nothing less than the manifestation of curved spacetime, bending the paths of objects along what we call geodesics. Consider another nuance. In the accelerating elevator, an ant crawling across the floor behaves differently than one falling through a vacuum. Its tiny legs feel weight just like your own, yet the curvature of its path is dictated entirely by the same local rules that govern your experience. From the perspective of physics, each object, regardless of size, composition, or complexity, is bound to the geometry of the space it inhabits. The elevator becomes a stage for a cosmic drama. Acceleration, gravity, and the motions of all objects are actors following the same script, a script written in the subtle language of space-time curvature. Einstein's brilliance lay in seeing the universal in the particular, the cosmic in the everyday. The elevator experiment is not merely a mental curiosity. It is a lens through which the unity of nature becomes apparent. By stripping away external references and focusing on local observations, he revealed a profound symmetry. Gravity is not a mysterious force tugging at matter, but a property of how matter interacts with the very stage of the universe. Acceleration is its twin, indistinguishable in local perception, yet inseparable from the geometry that shapes reality. Even more poetically, this thought experiment bridges the gap between human experience and universal law. It begins with a simple observation: weight, a feeling so ordinary that we take it for granted. It ends with a radical reimagining of reality, that the sensations of weight and the motions of free-falling bodies are encoded in the curvature of space-time, in the subtle, silent dance of geometry and mass. To grasp this, one need not see distant galaxies. One need only imagine the sealed elevator, suspended somewhere between certainty and possibility, and let intuition guide the mind to a truth more profound than any measurement alone could reveal. Thus, the logic of the equivalence principle is born from imagination, not instrumentation. It is a reminder that physics is as much about thought as it is about observation, as much about curiosity as calculation. The thought experiment of the elevator reveals a radical symmetry in nature, one that dissolves the boundary between gravity and acceleration and opens a portal to the idea that space and time themselves are dynamic actors in the cosmic story. In this quiet, hypothetical chamber, the universe whispers its secret, that motion, mass, and geometry are intertwined in ways that defy the ordinary, yet can be understood through the extraordinary power of human imagination. This is the spark that ignites the story of the equivalence principle. The realization that our everyday experience, so banal and familiar, is in fact a window into the profound. It is the curiosity that dares to ask, what if all forces of gravity are simply manifestations of how space and time bend beneath our feet? It is the itch in the mind that cannot be ignored, the quiet insistence that reality is more elegant than we have dared to imagine. And it is from this spark, this quiet philosophical unrest, that the journey toward understanding begins. A journey that will take us from the ordinary fall of an apple to the extraordinary curvature of the cosmos itself. Having glimpsed the spark of curiosity and felt the vivid clarity of the thought experiment, we arrive now at the core, the beating heart of the equivalence principle. Here, we leave behind the poetic musings of elevators and apples and enter the realm where philosophy and mathematics entwine. The question is no longer merely conceptual. It is a question of nature's very architecture. What does it mean, in precise terms, to say that gravity and acceleration are equivalent? At its essence, the equivalence principle rests upon a deceptively simple equality. The inertial mass of an object is identical to its gravitational mass. The inertial mass, m sub I, measures an object's resistance to acceleration when a force is applied. The gravitational mass, m sub g, measures the object's response to a gravitational field. Newton had treated these as separate empirical quantities, measured independently, and found them remarkably proportional. Einstein's insight was more audacious. This is not coincidence, nor mere proportionality. It is identity, a fundamental symmetry of nature. M sub I is equal to M sub G. This equality is the key that unlocks a radical shift in understanding. It tells us that an object's resistance to acceleration and its susceptibility to gravity are not distinct properties of matter. They are two faces of the same coin. The apple falls, the hammer descends, the moon orbits, all because space-time itself dictates the path, and not because of an external tug. To see this clearly, one must abandon the notion of gravity as a force in the Newtonian sense, and embrace the revolutionary idea that gravity is geometry in action. Imagine a free-falling observer in a gravitational field. To this observer, all objects nearby appear weightless, floating in perfect freedom. No forces are sensed. There is only motion along a natural path dictated by space-time. These paths are called geodesics, the equivalent of straight lines in curved geometry. In Einstein's vision, mass and energy curve space-time, and free-falling objects follow these curves. Gravity, then, is not a force pulling at objects, but the manifestation of the curvature of space-time itself. The equivalence principle is the bridge that connects our intuition about weight and acceleration to this geometric truth. One can express this interplay mathematically. Consider a small region of space-time, sufficiently local that tidal effects, the differences in gravitational pull across space, can be ignored. In this infinitesimal region, it is always possible to choose a reference frame in which the laws of physics reduce to those of special relativity. Locally, g mu nu approaches eta mu nu. Here, g mu nu represents the space-time metric in the presence of gravity, and eta mu nu is the Minkowski metric of flat space-time. In other words, locally, the effects of gravity can be transformed away, rendering physics indistinguishable from a gravity-free accelerating frame. The equivalence principle is the statement that such a transformation is always possible, and this is precisely what allows the formulation of general relativity. But beyond the mathematics, there is a cosmic drama playing out. Each object in free fall is a character in this story, tracing a path determined by curvature, not by invisible forces. The Earth, the Moon, the apple, the photon, each follows its geodesic with perfect fidelity. Even light, massless though it may be, bends when passing near a massive star, not because it is pulled, but because space-time itself is curved. The equivalence principle predicts this elegantly. All objects, regardless of mass, experience gravity identically, and all paths are shaped by geometry rather than force. Physically, this core insight has profound implications. The feeling of weight on Earth is not universal. It is the reaction force of the ground resisting your natural geodesic motion. A person in free fall, say an astronaut descending toward a planet, feels no weight at all. Gravity is present, yet absent. The distinction between being stationary in a gravitational field and accelerating through space is erased. The local laws of physics do not betray the difference. This is the essence of Einstein's insight. The equivalence principle is not merely a statement about masses. It is a statement about the unity of space-time, motion, and matter. At this core, mathematics becomes poetry, and physics becomes philosophy. A single equality, m sub I is equal to m sub g, cascades into a radical reconception of the cosmos. Forces are no longer fundamental, geometry is. Paths are no longer dictated by mysterious tugs, curvature guides every motion. And the mind that grasps this sees the universe in a new light, elegant, unified, and profoundly beautiful. The equivalence principle is not an abstract idea confined to textbooks. It is a lens through which the cosmos reveals its hidden simplicity, showing us that gravity, acceleration, mass, and motion are threads woven into a single coherent tapestry. This is the spark that ignites the story of the equivalence principle, the realization that our everyday experience, so banal and familiar, is in fact a window into the profound. It is the curiosity that dares to ask, What if all forces of gravity are simply manifestations of how space and time bend beneath our feet? It is the itch in the mind that cannot be ignored, the quiet insistence that reality is more elegant than we have dared to imagine. And it is from this spark, this quiet philosophical unrest, that the journey toward understanding begins. A journey that will take us from the ordinary fall of an apple to the extraordinary curvature of the cosmos itself. Once the core of the equivalence principle is grasped, the mind cannot help but wander outward, tracing the ripples it sends through the universe. A single, deceptively simple idea, that locally gravity and acceleration are indistinguishable, unfurls into consequences so profound that they reshape our understanding of the cosmos itself. What begins in a humble elevator or a falling apple extends to the orbits of planets, the bending of starlight, and the very fabric of space-time. Consider first the elegance of planetary motion. In Newtonian physics, planets are drawn around stars by a force acting across empty space. Yet, the equivalence principle suggests a more intimate picture. The sun's mass curves the space-time around it, and the planets are simply following the natural paths, the geodesics, laid out by this curvature. Their motion is not the result of an invisible pull, but of the contours of the cosmic stage itself. Mercury's orbit, which puzzled astronomers with its subtle precession, finds a natural explanation here. The tiny deviations arise because the space-time near the sun is not flat, but subtly warped. A problem that resisted solution for decades is resolved once we recognize that acceleration and gravity are reflections of the same geometric truth. Beyond planetary orbits, the principle predicts phenomena that challenge ordinary intuition. Light, which has no mass, should, under Newtonian thinking, pass straight through space, unaffected by gravity. Yet if gravity is curvature, then even massless photons must follow the contours of space-time. Starlight passing near a massive body bends, not because the star tugs on it, but because the geometry through which the light travels is curved. This prediction, confirmed by observations during a solar eclipse, is one of the most elegant demonstrations of the equivalence principle. The path of light and the path of a falling apple are governed by the same cosmic law, united by the geometry of space-time. Time itself is affected. Clocks in stronger gravitational fields tick more slowly than those in weaker fields, a phenomenon known as gravitational time dilation. An observer in a tall building experiences time differently from someone at sea level. GPS satellites, orbiting high above Earth, must account for this subtle difference, or their navigational calculations would drift by kilometers each day. Here, the equivalence principle underpins practical technology. The ripples of a thought experiment in a sealed elevator echo into the devices we rely on every day. Acceleration, gravity, and the passage of time are intertwined in a cosmic ballet that affects both the grandest scales and the minutest mechanisms of human life. Even more astonishing are the consequences in the realm of the extreme. Black holes, those mysterious abysses where space-time curves so steeply that nothing can escape, are direct manifestations of the principles Einstein unveiled. Objects falling toward a black hole are following geodesics of an extraordinarily warped space-time. Tidal forces, which stretch and compress falling matter, are consequences of curvature gradients, the universe's geometry revealing itself in violent, magnificent displays. Gravitational waves, ripples in the fabric of space-time itself, carry information across the cosmos at the speed of light, connecting distant events in a choreography only comprehensible once the equivalence of gravity and acceleration is recognized. Perhaps most profoundly, the principle reshapes our philosophical understanding of reality. Before Einstein, gravity was an external actor. After Einstein, it becomes the stage itself. Matter tells space-time how to curve, and space-time tells matter how to move. There is no external force pulling, there is only geometry, and our perception of weight, acceleration, and motion emerges from our place within this curvature. The cosmos is not a static arena in which objects play. It is a living, responsive tapestry, and we, in our small and ordinary ways, move along the contours it provides. The ripples extend further still into cosmology. The expansion of the universe, the formation of galaxies, the clustering of matter, all are governed by the interplay of mass, energy, and the curvature of space-time. The equivalence principle, by linking acceleration and gravity, allows us to describe the universe not as a collection of forces acting on isolated objects, but as an interconnected geometric whole. From the motion of quarks within atoms to the dance of clusters of galaxies, the principle is a unifying thread. In essence, the equivalence principle transforms our understanding of the universe from one of mechanical forces to one of geometric elegance. It is a single insight that radiates outward, influencing the motion of planets, the bending of light, the ticking of clocks, the behavior of black holes, and the evolution of the cosmos itself. From the humblest elevator to the most distant quasar, the principle is the invisible cord that binds together the vast, intricate symphony of the universe, revealing a reality far more elegant and harmonious than Newtonian intuition could ever have imagined. This is the spark that ignites the story of the equivalence principle, the realization that our everyday experience, so banal and familiar, is in fact a window into the profound. It is the curiosity that dares to ask, what if all forces of gravity are simply manifestations of how space and time bend beneath our feet? It is the itch in the mind that cannot be ignored, the quiet insistence that reality is more elegant than we have dared to imagine. And it is from this spark, this quiet philosophical unrest, that the journey toward understanding begins. A journey that will take us from the ordinary fall of an apple to the extraordinary curvature of the cosmos itself. At the heart of every great scientific insight lies the human element, the patient curiosity, the stubborn imagination, the unyielding willingness to follow intuition where convention fears to tread. The equivalence principle, for all its elegance and universality, was not plucked from the ether fully formed. It was born from the mind of a thinker willing to question what everyone else took for granted, to see the world not as it appeared in the textbooks, but as it truly might be beneath the surface. One must never underestimate the courage it takes to embrace simplicity in a world enamored with complexity. Einstein often spoke of the holy curiosity that drives a scientist, the quiet, almost sacred insistence on asking the questions others overlook. Why does an apple fall? Why does a feather fall at the same rate as a hammer? These are questions children might ask, yet in them lies the seed of cosmic revelation. To see such ordinary phenomena and recognize in them the blueprint of space-time is to engage in an act of profound imagination. It requires patience, rigor, and the willingness to trust intuition, even when it contradicts established wisdom. Consider the struggle inherent in this process. For years, Newtonian mechanics reigned supreme. Generations of thinkers had accepted gravity as a force acting at a distance, predictable, precise, unquestionable. To propose that gravity might be something entirely different, to suggest that acceleration and gravity were fundamentally indistinguishable, required not only intellectual boldness, but also a readiness to face skepticism. The mind must wrestle with its own assumptions, unlearn certainties, and hold in tension the paradoxes that defy immediate comprehension. This tension is the crucible in which insight is forged. The equivalence principle did not emerge overnight. It was the product of relentless reflection, countless mental experiments, and the courage to see nature as a whole, unified and profoundly elegant. And yet, there is beauty in this struggle. The equivalence principle is not merely a technical insight. It is a window into the poetry of reality. It reveals that the mundane, the feeling of weight, the act of falling, the motion of a hand against a book, is entwined with the cosmic. Every motion, every acceleration, every sensation is an expression of the underlying geometry of the universe. To recognize this is to see the world with new eyes. Each experience becomes a reminder of the hidden symmetries, the elegant structure, the dance of space-time that frames all existence. The principle invites us to marvel at the ordinary, for within it lies the extraordinary. Human curiosity is at once the spark and the compass. It allows us to pose questions that may initially seem absurd. Could gravity and acceleration be the same? And then follow the answers wherever they lead, even into realms that challenge our deepest intuitions. It is curiosity that drives the mind to invent thought experiments, to envision elevators floating in space, to imagine free-falling observers and bending light. It is curiosity that bridges the gap between childlike wonder and adult understanding, reminding us that science is not merely measurement and calculation, but a creative engagement with reality itself. Moreover, the human element emphasizes connection. The insights of one mind, Einstein's in this case, resonate across generations, inspiring others to explore, test, and expand upon them. The equivalence principle became the foundation of general relativity, which in turn opened the door to modern cosmology, black hole physics, and gravitational wave astronomy. The struggles, the patience, the imaginative leaps of one thinker ripple outward, shaping the understanding and experience of countless others. Science is, at its core, a profoundly human enterprise, and the elegance of the equivalence principle exemplifies how human curiosity can illuminate truths that are both universal and deeply personal. Finally, the human element reminds us of the joy inherent in discovery. There is a profound satisfaction in recognizing a pattern that others have overlooked, in seeing the hidden harmony behind apparent chaos, in knowing that the laws of the universe can be understood through reason, reflection, and imagination. The equivalence principle is a testament to this joy, a simple, elegant idea, accessible through thought, yet capable of explaining phenomena from falling apples to orbiting planets, from bending starlight to the dynamics of black holes. It embodies the wonder, the humility, and the boundless curiosity that define the human pursuit of knowledge. In the end, the equivalence principle is more than an insight about gravity and acceleration. It is a celebration of human imagination, a triumph of patience and reflection, a reminder that curiosity, coupled with rigor and courage, can reveal truths far greater than those apparent to the senses. It is a mirror in which we see the mind reaching outward, probing the cosmos, and finding elegance where others saw only complexity. It teaches us that discovery is not only about the universe, but also about the remarkable capacity of the human mind to perceive it, to wonder, and to marvel at its beauty.